Hello, everybody. We're going to talk about our neural super resolution and frame generation work that we've been working on for some time for mobile devices. Quick introduction from me. Rob will dive into some details on what we're working on, and then Matthew will discuss one of the use cases with Unreal Engine using our technology. So the challenges with mobile is a lot of the PC gaming type experiences are transitioning into mobile. Gamers want higher fidelity gaming, more resolution, and a lot of these kind of higher quality gaming is pushing mobile to its limits. On the other side, those limits are being hit with power and thermal. Gamers want longer duration sessions, so battery drain is a constant constraint, and thermal throttling is a real issue. If you're pushing the system to max load for a sustained period, you're going to hit thermal limits, and your gameplay experience is going to suffer. So we're really kind of balancing this quality, power, performance trade-off all the time with mobile gaming. And that's where we see this technology really helping the mobile gaming experience. Quick history on our prior solutions. Snapdragon Game Super Resolution was one of our first algorithmic solutions for upscaling. We've also introduced the Adreno Frame Motion Engine shortly after for 2x frame extrapolation. And we've iterated on these to the point of introducing temporal upscaling and motion vectors and optical flow with our frame generation. And the latest solution that we're going to discuss today is what we affectionately call our codename Adreno AI Frame Fusion, or AIFF, where we are starting to get into more of the neural super resolution and frame generation. So a little bit about high level about what we're offering is a 2x upscale and 2x frame generation, super resolution and frame generation, where super resolution, as an example, might be where your game can render at 540p and upscale to 1080p, or frame generation, render at 30 frames per second and get a 60 frames per second result. We're looking at how do we deploy this to the ecosystem and what are the components involved. And right now we're looking at our AIFF runtime, the AIFF SDK, game engine plugins for Unreal and Unity, our support in Snapdragon Profiler and our other developer tools for AIFF, and of course samples and documentation about how best to leverage and integrate AIFF in your game. Quality is something that we take very seriously for AIFF. We understand that as game developers, you may not be interested in using this if you can't provide the gameplay experience that you're looking for and the visual fidelity. This slide is just kind of talking about what are some of the approaches we're generally taking on this. We have a lot of internal content we're using to help train our foundational model. We are partnering with game studios globally to capture representative gameplay. And we're ensuring that we have feature coverage for our models on the things that they need the most. Thin geometry and foliage, particles and alpha, overlays, specular, and so on. From a validation standpoint, we're tracking objective KPIs as well as subjective expertise. While we're not going to share specifics about this information or these KPIs today, we can say that our model eval is hitting our internal targets with leading quality objectives. So we're pretty excited about this. This is AIFF in action. I've purposely not labeled it because we're going to have a little vote of which one is AIFF and which one is native. But this demo is an internal demo. You'll notice it's slightly out of sync. That's more of a technical issue with the capture. But this is an internal demo from our internal game studios team, rendering at 1080p on device. Oops, I was supposed to vote. Anybody cheat? I'm kidding. So on the left-hand side was AI Frame Fusion. You can, if you watch video, over time, you can notice where the artifacts are at. These are things that we're working on today. We're not publicly releasing this just yet. We're offering, kind of a teaser on what we are working on. And the native was on the right. So again, we're really excited about this. Rob and Matt are going to go into more details. So I will hand it off to Rob to start talking about the SDK.
Thanks, Kevin. I lead the AIFF software effort at Qualcomm, so I'll be talking to you about the software architecture, the SDK, and a little bit about the algorithms themselves. First, we start with the super resolution algorithm. The diagram has kind of the inputs and the outputs and the intermediates colored differently. So we start with a low resolution color, depth, motion vectors, and jitter offsets as inputs. This produces a high resolution color output. We also have a feature buffer that sort of comes out as well. And then we feed the feature buffer and the high resolution color back into the algorithm. That's what makes it a temporal super resolution algorithm. The network has 4 convolutional layers. These convolutions store intermediate results in Adreno HPM, or high performance memory. HPM is something we have in our GPUs that allows saving bandwidth to DDR and thereby optimizing performance and power. There's kind of more in the diagram here that you can look at offline, but I can't go into too much more detail on it here. There's also a white paper by our AI research team, if you take a shot of the QR code in the corner. On the other hand, our frame generation technology is completely proprietary, so we can't share a lot of detail about that here either. But it takes similar inputs to our super resolution algorithm, and it produces 1 intermediate frame for our 2x frame gen. It also uses HPM when running on the GPU and a similar local cache on the MPU. Okay, so for the SDK, the super resolution algorithm and the frame generation algorithm are provided as what we call techniques within the AIFF SDK. These techniques are kind of what you use to implement any sort of algorithm. The SDK, it uses Vulkan for the client API coming from the game engine, and the idea is we'll release this as an SDK that games can then integrate into their game and ship along with their game. When a when a game calls into the SDK to dispatch a technique, the implementation for that technique can run on either the GPU or the NPU. For the GPU, it kind of uses the standard APIs, and then for the MPU, it'll go through Vulkan data graph pipelines to execute the machine learning workload on the MPU. I think earlier Kevin sort of touched on our training methodology a bit. We're training the models, as much as we can with, internal and external content. But if for whatever reason your content doesn't run well on our model, we do have the capability for you to fine-tune the model weights and pass those into the SDK. Quick aside on Vulkan data graph pipelines. Our latest mobile devices all support the BK QCOM data graph model, BK ARM data graph, and BK ARM tensors extensions. These extensions allow you to run a workload on the NPU and sort of interop with it directly from Vulkan. So there's 0 copy buffers from the GPU to the NPU, and you can use all the standard Vulkan resources, synchronization primitives like semaphores, fences, everything you're used to in Vulkan, but actually dispatching the work on the NPU. The way that this works is you export your machine learning model in whatever format you want, Onyx, TensorFlow Lite, et cetera. Take that, create a graph pipeline using it, and then you can take that graph pipeline after it's been created and dispatch it through Vulkan using all the standard Vulkan APIs. There's a link here for reference to the Qualcomm extension. There's also an SDK that we've provided that sort of goes through the documentation for all of this and has samples. Okay, so back to AIFF. I have 2 slides with very detailed sequence diagrams that I'm not going to go through in detail. But the general gist of it is to give you an idea of the call flow for using the AIFF SDK. First, you create an AIFF instance. Then you query the requirements for the AIFF technique from that instance. And then that'll give you some extension, Vulkan instance and device extensions that then you have to enable when you actually create your Vulkan instance and Vulkan device. And then you create the actual AIFF technique. And then for each input and output resource, you go and query what particular attributes or requirements there are that are needed for that resource. So this can be usages or specific formats that are supported. And as long as you create the resource using those, then it should work with AIFF. And then per frame, it's as simple as setting up your resources and dispatching the technique and then submitting the work. And then on cleanup, it's just destroy technique and destroy instance. Okay, that's my last slide. I'm going to hand off to Matt for going through engine integration.
Hello, my name is Matthew Hoffman, and I'll be talking about how to integrate AIFF into game engines. I'll start with a high-level overview of how to integrate AIFF into a game engine. Then I'll give some details about how we integrated AIFF into Unreal Engine 5, and finally show some quality comparisons between AIFF and our existing temporal upscaler, Snapdragon Gaming Super Resolution. AIFF is still in active development, and some details may change between now and the final release. However, this should still provide a good idea of what it will take to integrate the feature into your game engine. AIFF works much like a temporal upscaler. It consumes the low-resolution color, depth, and motion vectors and provides an upscaled color image. If your game engine already supports temporal upscaling, it should be easy to add support for AIFF. The main inputs to the algorithm are a low-resolution color buffer in either high or low dynamic range, an inverted depth buffer, motion vectors showing the pixel motion, as well as the current jitter offset. And then your expected output is the upscaled color image in the same dynamic range as the input color buffer. So if you provide an HDR color input, you can expect an HDR color output. Note that any internal history buffers are managed by the SDK and do not need to be managed by the engine. There are some specific considerations that need to be taken into account when integrating AIFF. The first is that AIFF expects the jitter offset to be negated in both the X and Y directions before being applied to the projection matrix. The motion vector should follow pixel motion, so if your camera is moving right, we expect some negative values in the motion vector indicating pixels are moving left. The depth buffer should be inverted, and specific format requirements for the color, depth, and motion vectors can be queried via the SDK. Frame generation requires some of the same inputs as super resolution, namely the same low resolution depth and motion information with the same requirements mentioned previously, as well as the same jitter information. The main difference is it will take the full resolution color buffer after post-processing and for the best results prior to drawing the UI. And then the output will be the generated frame. Now we'll look into integrating AIFF into Unreal Engine 5. We will be providing UE5 plugins for AIFF, so the point of this section is not to provide a line-by-line description of how to integrate the feature, but rather to show how it can be integrated into an actual game engine. Unreal Engine 5 provides a temporal upscaler interface, which is how you add a new upscaler to the engine. In order to get to this, you'll first need to create a module interface. This is the standard starting point of a new plugin that manages the lifecycle of your plugin. Your module interface can then create a new scene view extension. This allows our plugin to interact with Unreal Engine 5's scene view rendering, and importantly here, allows to set a new temporal upscaler. We can then implement a new temporal upscaling interface that will hold all of our AIFF specific logic. The UE5 rendering pipeline will begin as usual with the view geometry rendering. We'll do our shadows, G-buffer, and lighting rendering all at the lower resolution. We'll then execute AIFF to upscale the color image from the low resolution to full resolution. We'll then pass this off to post-processing to do things like motion blur, bloom, and tone mapping before drawing the UI and displaying the final frame. Unreal Engine 5 does not maintain a traditional motion vector. Instead, it has an encoded velocity buffer that holds motion information for dynamic objects in the scene, which we will need a short pass to convert into the motion vector that AIFF requires. To do that, we'll first read the encoded velocity value, and if anything is written at a particular pixel, we use a built-in UE5 function to decode it and get the motion for that pixel. If there is nothing written into the encoded velocity buffer, we'll need to calculate the motion for static objects using information from the current and previous camera. That camera information will be jittered, and so we'll need to remove the current jitter offset in order to get the unjittered motion, before finally scaling by the render dimensions in order to get the pixel motion. As I mentioned, AIFF expects the jitter offset to be negated in both X and Y before being applied to the projection matrix. By default, Unreal Engine 5 only negates the Y component. So prior to Unreal Engine 5.6, we will require a small engine change to support negating the X component. However, in 5.6 and later, this can be handled entirely within the plugin. Finally, as Rob mentioned, the SDK may require certain Vulkan extensions to be enabled to function. This can be handled within the plugin by adding them to list in the startup module function in the module interface I mentioned. This is executed prior to Vulkan instance and device creation, so any extensions added here will be properly enabled when a Vulkan is set up. So to give a high-level overview of how you can integrate AIFF into Unreal Engine 5, we'll first set up Unreal Engine 5 by creating our module interface, our scene view extension, and our temporal upscaler. We'll then set up our SDK by creating our instance, querying the available techniques and the requirements, adding our Vulkan extensions, and finally creating our AIFF techniques. And then on the temporal upscaler add passes function, we'll add our pass to convert our velocity buffer into a full motion vector. We'll prepare our inputs to be consumed by the SDK, and finally dispatch our AIFF SDK techniques. The pipeline for frame generation looks much like it did for super resolution. However, after post-processing but before drawing the UI, we'll dispatch a different AIFF technique to generate a new frame. We'll then draw the UI on that frame and then display it before doing the same thing for the original rendered frame. Note that Unreal Engine 5 has built-in mechanisms to handle frame pacing such as swap EVK to help keep frame time smooth between the generated and rendered frames. Next, we'll look at some quality comparisons between AIFF and our temporal upscaler Snapdragon Gaming Super Resolution, or SGSR2. We'll be primarily looking at upscaling from 960 by 540 to 1920 by 1080 using SGSR's performance preset. However, we'll also sometimes be looking at SGSR's ultra quality preset, which renders over 2.5 times the base number of pixels. In this first example, we'll be looking at the Explorer descending down from the ceiling, primarily focusing on the water falling around him. You may be able to tell in this first image that the Explorer is slightly more clear and there's less ghosting in AIFF compared to SGSR in performance mode. But to really show the advantage of AIFF, we'll want to focus in on some of the falling water. Looking at the top of the frame, the water in AIFF is very clear and distinct. It looks like water falling down. SGSR struggles to upscale with so little pixel information, so the water looks smeary and more like an artifact than an actual intentional part of the scene. Looking at the bottom of the frame, we can see this trend continue. AIFF has very clear streaks of water coming down, while SGSR has blurred a lot of it in with the surrounding environment. Switching over to the ultra quality preset, we can see that the water is more distinct now in SGSR, but you may be able to tell that it is blockier and much noisier. AIFF preserves the original look of waterfalling much better in this scene. Next, we'll be looking at this scene, particularly focusing on the monsters in the background as an example of a detailed object in a dark environment. Looking at the closer monster, we can see that the monster itself is better defined with AIFF. There is less blurring around its edges. The details of the monster are also better defined. Its teeth and mandibles on its mouth are very distinct and clear, while they are blurry and hard to make out with SGSR and performance. The texture on the monster is also much better defined, with many more of the original details preserved with AIFF, which are lost in SGSR performance. Looking at the further monster, we can see these same trends continue. The texture on AIFF is much more clear and much more detailed, while SGSR performance has it blurred out a lot. You can also tell that AIFF has preserved individual mandibles around the mouth of the monster. On SGSR performance, they have blurred together into a single blob. Switching over to SGSR Ultra Quality, we see that some of the texture is back for the monster, but the mandibles still have an issue on SGSR, where they're still very blurry and hard to make out. AIFF handles these fine details much better. Next, we'll be looking at this scene of the explorer walking down the hallway, focusing on the holographic crystal with text floating around it. AIFF does an excellent job at upscaling this image. The crystal is largely free of artifacts, and the text is clear and sharp. SGSR performance struggled a lot. There's a lot of artifacting in the text, and some of the background color has blurred in with the crystal color. SGSR Ultra Quality has handled it better, but there is still more artifacting there in the text than in AIFF. Next, we'll be looking at this scene of a dragon landing on the cart. This is an example of a detailed object in a bright environment. In this scene, it looks like AIFF is rendered at a much higher base resolution, even though AIFF and SGSR performance share the same base resolution of 540p. Everything is sharper and cleaner using AIFF. Focusing particularly on the dragon, we can once again see that the texture on it is much more detailed with AIFF. The lines on the belly and neck of the dragon are much better defined. You also can probably see that the face of the dragon is much cleaner in AIFF, where things like the jawline, teeth, and eyes have blurred together using SGSR performance. Switching over to Ultra, the dragon's face is now clearer, but again, the texture on the dragon is much blurrier, and a lot of those details are harder to see. I don't know how well it'll show up on the projector, but the texture on the wings is also significantly better in AIFF, with the fine details of the veins in the wings much cleaner compared to SGSR, even with Ultra Quality. Next, we'll be looking at this scene of a monster attacking a city as an example of a high contrast scenario where the monster is dark compared to the surrounding environment. SGSR performance struggles a little with this, as it blurs a lot of the monster in with the surrounding background. The monster almost seems to fade into the scene. AIFF, meanwhile, makes it stand out as its own distinct aspect, a real menace that's meant to be in this scene. SGSR Ultra Quality, meanwhile, does make it stand out a little more, but AIFF continues to have a much cleaner texture on this monster. SGSR has introduced a lot of noise into that texture that AIFF has upscaled cleanly. Finally, we'll be looking at this scene of focusing on the destroyed building in the upper right of the frame. AIFF handles the thin geometry here very well. The pipes and wires sticking out of the building are clear and well defined. SGSR performance struggles a lot. There's a lot of gaps and pixels, and the top of this frame is very blurry. SGSR Ultra Quality has a lot of aliasing on the small, thin geometry and a lot of blurring in the top of the frame again. Both older SGSR implementations also suffer from a lot of noise, particularly a lot of small fireflies introduced throughout this frame. AIFF does not have that problem. It has created a much less noisy, much cleaner image. Thank you, and stay tuned for more updates about AIFF in the future.